So, am I on? So a couple years ago, at this conference, I mentioned that my daughters look for me on YouTube or Google and find my videos on YouTube and watch them. So a couple months ago, they actually came across the video where I said hi to them, and they were very happy. And my wife was like, "Where's my shout out?" So what I wanted to look at was where we she never searches for me, so where are we really going with LibFabric? And this focus of this presentation will be where are we going really in this next year. And looking back a little bit, so we just had the 1.6 release last month. If I look at what we did with the 1.4 release, 1.5 releases, we had a couple of point releases for both of those. I do anticipate with 1.6, we already have some bug fixes that came in, mainly around dealing with older compilers. So I expect we'll have like a 1.6.1 release probably this quarter, maybe a 1.6.2 release, and then we'll look at a 1.7 release somewhere towards the end of the year. And a lot of what I'll talk about in terms of the features are what's going to end up going into that 1.7 release. So I'm looking at really what are we doing in the provider space? What sort of features are we adding to either help providers or and what can applications do with them? And then look at where we think the APIs are going. What do we want to take LibFabric and what sort of features are we looking at trying to address? And then I have a couple of slides at the end dealing with what I'm calling companion APIs. I don't know if we'll get to that material because of time, but that will talk about like the C++ work that we're looking at, and also R sockets. But those slides will be available to go look at. I'm just not sure if we'll get to them in the talk. So in the provider infrastructure, so the RxM provider, again, this is doing reliable datagram semantics on top of reliable connected. So this provider is considered a fairly high priority for Intel and others in the industry. This is our primary path that we're using for HPC applications, MPI, SHMM, Chapel, Charm++, UPC, to access what we consider the verbs-based hardware. So all verbs-based hardware, whether it's InfiniBand or Rocky or iWarp, end up getting access through this RxM provider. And that's doing connection multiplexing. So this is layered. It's not just over verbs. It also works with targeting the network direct. So this is our path to supporting MPI on Windows. And we're looking at a TCP provider. So in the past, I've talked about within LibFabric, we have a sockets provider. And the sockets provider was designed mainly for filling out the API, for testing, evaluation, to debug with. It's since shown that people really like having access to just standard TCP through LibFabric because they can take sockets code out of theirs. So we're looking at taking the RxM code base, layering it on top of a TCP provider where the TCP provider simply does reliable connection, which maps well for TCP. And the goal here is to replace sockets provider with TCP, and hopefully that provides us better performance and it's more maintainable because we can design the TCP provider for performance up front. And we've already done a lot of effort with RxM to focus on performance. So ARUN and DMITRY, I have mentioned up there, do most of the work on here. They've done a lot of work looking at performance, especially DMITRY because he's from our MPI team. So he's looked at the performance. We say at this point we have very strong MPI performance, especially relative to where existing products are. And we are considering, we're in the same code base, right? So this is all LibFabric. We have access to verbs. We have access to network direct. Even though RxM looks at what the provider gives us, it doesn't make the direct calls to verbs, right? It's calling, the RxM provider calls LibFabric internally. So it's going through LibFabric to access all of the features. And that makes it very flexible. That means it can run over any provider. RxM can run over verbs or network direct or TCP. But we want to look at, if we have tighter coupling, where do we want to make select on our send path or our completion path? Go down to verbs directly or go down to network directly. And can we get some optimizations there? Really looking at, can we tweak out the code path? The RxD code, Brian mentioned this, so this is reliable datagram over datagram semantics. So we have an RxD provider that's upstream. It's been disabled. So it was disabled for stability reasons. We're looking at doing basically a redesign and reimplementation of the RxD provider. That's going on now. We expect that this provider would probably be upstream for the 1.7 release. So this is our path that we're using for HPC applications to basically provide scale. So once we get around about 1,000 nodes, so over 1,000 nodes, most of the MPIs, we have to switch to an unconnected communication model. So the RxD provider would layer over verbs UD queue pairs. Obviously, this would work well with US NIC. We have a UDP provider that could layer over. And then when we look in the future, we see, what if we had raw Ethernet, something like DBTK? We could layer RxD on top of just a raw Ethernet device as well. So this becomes that fast path that Brian was talking about to, if I can have a very simple piece of hardware, just raw Ethernet, plug it into the system, and then I can have full support for libfabric. Right? So you can get that up front, and then you can start optimizing for the hardware at that point. But at least you have something up and running quickly. Shared memory provider. So one of our developers, Alexia, she wrote the shared memory provider. She's one also working on the reliable datagram. So this came in the 1.6 release. We'll probably expand a little bit for the 1.7. So the shared memory code, again, it's upstream. This is a standalone separate provider just for local communication. This uses the Linux CMA cross-memory attach to do transfers. So this is limited to Linux. There is a component of the shared memory provider. There are some shared memory primitives. So if a provider wanted to pull in some of the shared memory support into their own provider, we at least provide some very simple primitives that they can use to kind of build this out. The shared memory providers, when we designed it, it did look at, if we're looking at 48 or 96 or 100 cores on a system, make sure that we can actually scale the shared memory provider. So we try to avoid, connections, even kind of virtual connections between peers. So we have single sets of command queues. We have the data transfers adjust based on sizes. So we have different protocols to transfer data between the peers. We may use CMA. We may do direct data copies into either the peers, what we call inject buffers, for smaller transfers, where we may just place the data directly into the peers command queue. And again, it changes the semantics in terms of the protocol and how quickly we can get acknowledgments back and what the completion model ends up looking like. For 1.7, we've done some experiments with using XPMEM. I can say at this point, for somebody who's not familiar with using XPMEM, it is not intuitive. So it was actually fairly hard to figure out, where do you get XPMEM from? Like, where is the official repository? How do you install it? Right? For somebody who's completely unfamiliar with it, it was actually fairly challenging for them to figure out how does XPMEM work. But we're hoping to have that in within the 1.7 release. A couple other provider areas. We did look at adding internal APIs. So these are not exposed to the applications, but at least into the providers. We have a memory registration cache and something we call the memory monitor. So the registration cache is obviously just caching registrations. We tried to define these APIs so that they could exist and work well. We don't have to change them, but because they're not exposed, we're allowed to. So from the provider's viewpoint, they provide an address, they provide a link, they simply check the cache saying, I need a memory region associated with this address. Is it already cached or not? The cache can return that. Because the cache is generic, if it doesn't have a memory region already associated with it, it uses a callback model back to the provider to say, you wanted a memory region, I don't have it, what do you want me to do with this? And this allows the providers to actually implement the registration. So the cache is generic in terms of the hardware, and then the provider would have to implement the callback pieces. For example, add a memory region. Most of the providers are going to simply just register the memory. Register memory, we store it. We have some accounting inside to know whether or not the memory region is actively used. Once it's inactive, we have a least recently used list that we maintain. And we have some parameters on the cache in terms of how large do we have a maximum size, for example? Once we go beyond a megabyte or 10 megabytes or a gigabyte, we don't want to cache the data, cache the registration. We want to register it. As soon as the application says, I'm done with the memory region, deregister it. We also have limits on how much memory will the cache maintain. So we don't want to cache more than, say, 4 gigabytes or 2 gigabytes. And once we've registered more than that, we simply stop caching those registrations and back them off. There are some other features we have built into the cache. For example, if we have regions that overlap, we automatically merge them. Again, this is selectable because we found certain benchmarks trying to merge regions actually causes the benchmarks to perform poorly. But there are cases where, if we have a region, another region close to it, we'll re-register that as one bigger region so we can handle larger transfers that hit in that same memory space. Obviously, the problem with caching is still that, what happens if the memory changes? The application frees the memory, or the virtual to physical addresses change. So we have this object we call the memory monitor that provides input into notifying the provider when there's been a change. So the memory monitor looks for events on the memory, any address, any length, anything that's changed, the page, the virtual address mappings reports back to this notification queue so that we know that from the registration cache, we need to remove that from the cache and re-register. And we have a kind of this plug-in design where a provider or a general core code within libfabric can plug into the monitor to report these events. So Crave, for example, in their areas, they have a plug-in piece that they use, proprietary plug-in that reports the memory mapping changes. So we have a very simple one that simply hooks malloc and free that works okay in a benchmark. And what we're really looking for is a generic solution here. Right? We've had it in the past, we've talked about, can we have MMU notifications go up from the kernel up to user space? So if we could hook that in, for example, directly into the Linux RDMA core through maybe the new ioctl interface, then we could actually plug it in to this framework, and we would have a very easy way to be able to have a registration cache and flush those entries out whenever we get notification that there's been a change. Performance monitoring. So this is another set of features that we've added. This is not hooked into any provider, so we have this basic functionality there. It was there for 1.6, but nothing actually is using it yet. This is based on using the Linux read performance monitor counting. So we have a set of APIs that allow us to basically do inline performance tracking. I have a slide coming up showing how we might be able to use this. So we defined in terms of performance management unit, we have what we call different domains. CPU domain, cache domain, could have a memory domain, the NIC. A couple examples we have up there is the CPU domain has different counters. It has cycles. It has instructions. Caches has 2 counters. We defined hits and misses. Right? If you go look at the RDPMC stuff, there's several different options here. There's more domains, more counters. These are the ones that we defined in a way that's easy for us to use. From the provider's viewpoint, they would create what we call this data set of performance data. And this opens up basically a single counter to look at. So say I want to know my CPU instructions. So they open up a data set for CPU instruction counts, and they want to have maybe 3 options. So I want 3 sets of data here. So they would have maybe count, I want to count how many instructions are in my send path, how many instructions are in my receive path, how many instructions are in my completion path. So we can hook these performance monitors in, do the counters to be able to do tracking in terms of how many instructions are in each of those code paths, and then we can get that data as output and analyze the results to see what sort of changes should we make. Are we actually making an improvement if we make this change to the code, or are we actually hurting the code? And one of the areas we expect this to be used is this new provider that was added in. It's not enabled yet, called the hooking provider. It's a horrible name, but it's the best I could come up with. So the framework for this is done. The concept of the hooking provider is if it's not enabled, it has 0 impact. Right? It's not going to do anything to the code. It won't have any impact on performance. But if you enable it, then it basically intercepts all calls to a given provider. Right? So you enable the hooking provider. Again, the libfabric interface uses function pointers basically to do everything. So as long as you're not doing the static linking, you could enable the hooking provider. It'll inject itself in between all the calls to a provider and allow us to do some sort of operations on it. For example, I can update the hooking provider now to add in this performance counters. So you can write your provider, you can load the hooking provider with the performance option, and the hooking provider can automatically count these instructions for you, or count how many CPU cycles occur on these different data paths. Another use for it would be, I want to launch the hooking provider, but set it for a debug mode. So now even during a free build of the system, or release build, I can have the hooking provider there, load it, and always have debug information available to at least track through the calls and what's occurring. So I expect within the 1.7 release, we'll actually enable this, set it up to use these performance counters, probably some debug capabilities, and then we can start expanding what this hooking provider can do. API exploration. So that's kind of where we are with the providers. And what we're looking at with providers, this is looking at what are we going to do with the APIs. I actually have a provider slide down here too. So the first thing I looked at, and this is already upstream, the definition for this anyways, is something called variable length message. And this actually came out of looking at the implementation of doing 0MQ. So Kayla, who's actually back here, was working with 0MQ. And one of the things that we were running into was what the applications are wanting to do is they want to send a message to the peer, and the peer wants to receive it, but the peer has no idea what size the message is. Now, it took us actually looking at the cloud and enterprise space to realize this, but HPC has the same problem. We just had solved it already, so we didn't really analyze what they were doing. So we want to have this concept built into libfabric is I want to be able to send a message, but I don't know how big it's going to be. I want the receiver to get it. Well, there's several ways this has been handled. Right? The most common one is this eager message rendezvous protocol, where it says, OK, I want to send a message. If it's a small message, say 4K, 8K, it's an eager message. Just send the 4K or 8K to the peer. They have the receive buffers posted, so they'll get the message and then report it to the application. Well, what if I have a larger message, 16K, 32K, megabyte, gigabyte? They switch to the rendezvous protocol. And the rendezvous might be, I'm going to send just a notification saying I have the data. Right? Over verbs, you might say, I'm going to send the data, I'm going to send the key and an address. Right? So the peer then does RDMA read to fetch the data across the network and then reports the data. Right? That's one way of implementing how you do this large message transfer. If you didn't have RDMA-capable hardware, you might use a tag message feature. So you still may use an eager message, but your rendezvous may change in terms of the protocol to do a tag message where you, on the receiving side, post a message with a tag, and now the peer can send a tagged message across. Conceptually, it's very similar, but the wire protocol does change. When I mentioned this RxD provider, right? Well, how would RxD provider handle it? So I'm doing reliable datagram over datagram. Right? It doesn't do RDMA capabilities. So maybe it does a different protocol where it says, I want to send an MTU size message. That maps well for doing datagram transfers. The peer would naturally, as part of their protocol, maybe do some sort of flow controller windowing. So it gets the first packet of the message. The first packet of the message says how big it's going to be. It can set up the receive buffers. It can allocate the window that it needs and send back an acknowledgement to the peer saying, OK, I'm ready for the other parts of this large transfer. Again, conceptually, this is kind of like a rendezvous. But again, the implementation is very different underneath in terms of what you see on the transport layer. And what we're finding is that because of this feature where I don't know how big the message is at the receiving side, you have the same implementations being done at multiple levels. So we looked at inside libfabric, we have this sort of rendezvous protocol. Right? RxM provider does this sort of protocol. The RxD provider is going to do something very similar. And then we look at MPI. MPI re-implements this. Right? Again, and we looked at Shemem. Shemem implements this as well. Charm++, they implement rendezvous again. Right? So we haven't actually removed this feature of having to implement rendezvous multiple times. So, and the other problem we wanted to address with this sort of feature is most of these applications don't have limits on how large the messages can be. So the transport may say, I can't take anything bigger than 2 gigabytes, or maybe 4 gigabytes. But from the application, they have a 32 gigabyte transfer. So I want to send 32 gigabytes. Well, how do you send 32 gigabytes over a transport that's only supports 2 or 4? They end up doing a rendezvous type protocol again. So we want to try to capture both of those requirements, and the feature we picked, called it, was variable length message. So how does it work? Right? Obviously, this is an opt-in type model because this does change something at the protocol level, where the application says, I want to send a variable length message. The receiver is going to receive notification of, hey, I've got to receive. I know the size of the message. And now at the receiving side, it just says, I need to go allocate my receive buffer, wherever it is, come back down to the API and say, claim the message. So we already have this sort of feature in libfabric when we're dealing with tag messages and unexpected data. We have this concept of a claim discard feature, where a message arrives at the receiving side. The receiver either claims the message with the buffer and says, I want to claim the message, put the data in this buffer, or it simply comes down and says, I don't need this message anymore, discard it. So we simply expanded that, not just to unexpected tag message, but any tag message and any normal send-receive message. So now from the application's viewpoint, they can send any size message. The receiver is going to receive that message of that size, and they don't have to implement rendezvous. So only these provider people under libfabric actually even know how to spell rendezvous now. So everyone above is free from having to learn it. So one of the things we looked at with this is, OK, we have this discard message. And this actually came up in the working group. Is on the send side, if the receiver discards the message, do we notify the sender that the message has been discarded? Well, the current semantics are, no, we don't. We simply discard it at the receiving side. The sender, their completion doesn't change. But what if we actually propagated that discard back to the sender? For HPC, there's probably not a strong use case. But for enterprise or cloud, there may actually be. Right? If I have a client, or say a bunch of clients, sending to one server, and they all send messages to that server, and that server all of a sudden gets overloaded. Right? It wants to start discarding messages. So, OK, I have too much data here. If they could discard the message, have that discard go back to the sender gets some sort of busy completion. Now the sender can either retry to the same peer, or maybe the sender redirects the request to a less busy server. Right? So this is a feature we think that maybe applications could take advantage of if the sender could actually get busy notification. And then that led to an opportunity of saying, well, why should the application actually have to go through the process of saying, get a completion, look at the message just to say discard? What if I had an auto discard feature? Right? Can I set at the fabric level, as soon as the server realizes I'm busy, I am too busy to deal with anything, flip a bit that says discard every incoming message. Now every message that comes in, as soon as the message is starting to be received, the fabric could kick back another response saying too busy. Either redirect to someone else, or you'll just have to wait until I can get to the message. So that's something we're looking at. Do we want to have this busy type propagation going back to the peer, and how do the applications make use of it? Multi-rail provider. So Brian mentioned this. We are actively implementing the multi-rail support. Features we're looking at was, say, people wanted to have increased bandwidth. They wanted to increase the message rate. So when they asked to increase the message rate, again, that changed the design of what we would do with multi-rail. And they wanted to be able to have failover. So they wanted to have some number of active ports, some number of standby ports, and either have the standby kick in as soon as one active port fails, or maybe you want to have all the active ports fail before going to the standby port. So the multi-rail provider is trying to do both of those. And we also even had a request to say, what if I'm not even dealing with multiple rails? What if I just want to have multiple endpoints out the same port? I need multiple TCP connections to get full bandwidth. So we wanted to make sure the multi-rail provider has that capability as well. So the multi-rail provider, you can want to look at the code. It's actually starting to go upstream. It's layered as a utility provider. So it's layered on top of libfabric itself. So this is very generic. So it could work with any providers. It doesn't even need, on the railing, it doesn't even need the providers underneath to be the same. So conceptually, this could have for example, your active rails could all be InfiniBand. And then if those all fail, your standby could actually be a TCP Ethernet connection. Right? So you would have the ability for multi-rail to just fail over between providers even. So one of the features that we're going to use with multi-rail is this variable length message support. Right? We found when we looked at implementing multi-rail, what are we going to have to implement? Well, as soon as we started trying to do the implementation and design, we're going to have to do rendezvous again. We said, well, let's push that down because we've already done rendezvous in the underlying providers. So we want to have multi-rail configured by an administrator. So you could basically set environment variables to say, what are the active rails, what are the standby rails, and let the administrator just program those in. We also want a way for applications to specify this and have full control. So we're looking at doing both of those. For applications doing full control, obviously the application is going to have to be multi-rail aware. But we already have the capabilities within the APIs to be able to support this. We have these, what we call it, FI info structures, which is each info structure describes basically a single rail. And we just need to provide a list of these from the application back to LibFabric to say, here are my list of rails I want, and here are the low-level details of how I want those rails configured. Missing piece of this is how do we handle recovery fallback? So once we've gone from an active to a standby, how do we go back to an active? And we're not sure how we end up dealing with that. There's been a lot of suggestions from people. How do we plug into like PMIX, for example? How do you actually detect that a rail is no longer down? Persistent memory. So this is something that we started adding into 1.6. We expect it to be expanded. So the 1.6, we added just a couple of very small little pieces. We wanted to start somewhere, but at least now we have something that we can deal with persistent memory. We added a new, from LibFabric's viewpoint, a completion semantic. So LibFabric defines when you get a completion locally, what does that mean? So we defined this commit complete semantic that says when I do an RMA write, for example, and I have commit complete, that means that write is persistent at the peer. That I've actually hit persistent memory, the data is set there. I'm not going to lose it after a power reboot. The other change we ended up making with this is the applications we believe need to be persistent memory aware. So we added to our registration code that when an application registers memory, they indicate whether or not the memory they're registering is persistent or not. So we're not relying on the provider to have to go figure out, are you dealing with persistent memory? We could, but it would be a lengthy overhead to actually go check every page to see is any of this memory persistent. So this is our first step. We think there are going to be more APIs that come out of this. Documentation, we limited the use case to basically just RMA write operations to persistent memory. But again, that's just for documentation. From the API, there's nothing that prevents, for example, atomics. Do I want to do atomic operations to persistent memory? Does that make sense? When we look at the persistent memory, the biggest challenge that we end up facing is how do we keep the implementation agnostic? I mentioned a lot of the applications, they want to be able to just run on LibFabric because it supports sockets, and if they don't have the advanced features, fall back to just a TCP mode. So when we get into a persistent memory case, we need to be aware of, are we dealing with transport-specific features and basically a hardware NIC that's plugged into the same PCI slot as persistent memory, or do I have some sort of on-load model? Again, that changes what we need to do. I can't necessarily rely, if I keep it implementation agnostic, if I fall back from, let's say a InfiniBand or a Rocky device that can do access to persistent memory, and I have to switch from that mode to a TCP model, where now I'm having to do persistent memory accesses through a CPU, what does the API change look like? We want to make sure that we can be efficient in both of those cases. Right? We don't necessarily want to have huge lists. If I want to track every memory RMA write that I did and have this huge list of RMA writes. At the same time, we don't want to have it where we disable a feature, say that InfiniBand comes up with, that we can't take advantage of that hardware. So we want to be able to take advantage of the hardware, but also be able to switch back to this other mode of having partial or full on-load capabilities. And multi-rail. If I throw multi-rail into the equation, how does that change what the semantics look like, just in terms of the implementation? And hopefully as we work with the SNE organization, we can get more details as to what we want this to look like and what sort of application characteristics are we looking for. But I think it'll be challenging because of this. So the last slide I'll cover for today. So this is, if we step back and look at not just persistent memory, something I'm calling data domains, making up this term. If I look at our RDMA operations, there's really some assumptions built into this. One is that I'm dealing with memory mapped regions. Right? In order to register memory, I have to have that memory space in my virtual address space. So I'm dealing with memory mapped regions. Then I'm also cache coherent. So if a peer does a write to my memory, and I go from my CPU and go read that same address, I should see that update. Just accessing CPU load store. Well, what if we try to break some of these semantics? Are we constrained to do memory mapped regions? What if I'm not? Right. If I have a persistent memory, do I have to have that persistent memory space memory mapped in? Or is there a way for me to do an RMA to persistent memory without actually memory mapping it in? And what does that look like in terms of an API? And peer-to-peer transfers. Right? I may be in a completely different cache domain. So if I want to have an RDMA hit the NIC and go to a peer device, say a GPU, do I need that peer device memory mapped in? Or can I just have some way of accessing through the NIC to go directly peer-to-peer? And do I have to do anything else to the application to resync CPU caches with these accesses? Or if I'm updating persistent memory, can I update persistent memory without touching the CPU caches? Maybe the application doesn't care about the memory. It just needs to set it up so the transfer can occur. I want the data to go to the persistent memory. I don't care about it going into my CPU caches and flushing them out. So I'm not sure what those end up looking like. I just think that these are areas that we're going to have to look at in terms of how do we deal with peer-to-peer transfers or persistent memory and not always being in a cache coherent situation. And then how do I take advantage of something like a smart NIC where I have programmability? Right? Maybe I want to do encryption or decryption. Now, there could be any number of things you want to do on your data flow on either outbound or inbound. How do you specify those in a generic fashion? Or can we even try? Right? Does this become, once I deal with this FPGA type stuff, it all becomes vendor specific? Or is there something we can do there to actually help? So this is an area where I don't really have a clear picture of what we'll end up doing with these sort of APIs, but I think we need to look at this and maybe try to come up with a plan for the 1.7 release. So the companion APIs, I'm going to skip this. So C++ standardization, there's going to be a BOF later today that I'll talk about the C++ in more detail. And then RSockets is something we're also looking at. Do want to mention with RSockets that there is an effort to actually bring RSockets into the open Java development kit. And that's all I have. Any questions? Yes, I'm president and CEO of my own little world.
Excellent. Hey, you mentioned persistent memory support, and you said the memory registration would be extended to include what I understood was a Boolean, saying it was a persistent region. Is a Boolean enough, and what actually do you use it for other than like tracking writes?
So what we added for persistent memory today is basically just a flag to indicate that the registration is, the memory region is going to persistent memory.
But that, you had many examples of what that was, right? Device memory, host memory, what type of memory. Is a Boolean enough to describe what is what drove the current changes to the API was looking at the lib-rpmem use case. So we looked at what that use case was, and then we tried to create APIs that would match that use case. So that's where it's kind of designed around. Whether it's enough or whether we need more, I don't know. Go ahead. So it's probably not enough. The SNIA twig will probably give you lots of input. I'm assuming you're proposing working with the twig from the OFI sort of perspective, right? Under this new Alliance
Correct.
Umbrella. Okay, great.
Yeah.
It'll be a great.
We expect that there'll be more use cases than we have.
So imagine I have a a cluster that has a high-performance interconnect, and then I have a storage fabric that might be InfiniBand, and I might have another, Ethernet, and I want to use OpenFabrics or libfabrics across all of these. Have you considered any kind of a routing daemon or routing service, something like Elnet has for Lustre?
We have not looked at any sort of routing between different fabrics, no.
Please think about it.
So. Thanks.